Come on.
Okay, so welcome to this first guest lecture in the course. So we have Ehnberg here, who will tell us, he's an expert on power engineering. He will tell us a little bit about the application and also a little bit how communication plays a role in this one. So thank you very much for agreeing to this.
Thank you.
Go ahead.
Good morning, everyone. My name is Ehnberg. I work as a researcher at the Division of Electric Power Engineering at the Department of Electrical Engineering. My role here today, I was asked here to come to talk a little bit about this ICT and this new role, because it's quite new in some aspects at least. I will try to put more emphasis on the role than actually what kind of communication there are. And that is for a few reasons. The main reason is that we don't really know, because it's not really there yet. So we haven't established which communication to use, what kind of speed do we know. And the other reason is that it's not really what I think it's funny. So I'm more trying to describe what I want, and you have to solve it. And also, I will also go a little bit into what happens if we don't solve it. You might have heard the news that there was actually a quite big news related to this issue. I think it was yesterday or today about Svenska kraftnät. I will come back to that later. So therefore my presentation was really updated because it happens very recently here. But so far. First I would like to give some kind of background. What are we talking about? We are talking about a big system. Sorry. We are talking about quite a big system. I have put in some numbers. Those are only numbers in Sweden. And we know that Sweden, even though it's a big country, it's nothing compared to the rest of the world. But still, we get power lines. If you add them on top of each other, they will last 13 laps around the world. So it's there is a lot of them. And this is the problem, of course, because you can't measure in one point, because it's a lot of different levels. I try to divide it into 3 different levels. I will come back to those later. And you see, the further down you go, transmission, this is the big lines you see. We got 15,000 kilometers. Feels long, but it's practically nothing compared to the rest. Subtransmission, regional grids, a little bit bigger line. Distribution, that's inside towns. And then we got the local one, which also the kilometers that you have at home. You see, do I have any power system? Yeah, you have quite a lot. Because from your connection point to each outlet, through some kind of switches, you might want to turn off and turn on the lights. There is a lot of lines, and those will be affected, and they will be part of the power system. They are a part of the power system, and they will continue to be, so we have a lot of them. In Sweden, we have 5.5 million customers. That means, a family house, that is one customer, but also industries, Chalmers is one, so there is quite a lot of those. In Sweden, we produced 159 terawatt hours of energy. So you can also see the value of that. It's a quite big industry that needs to be run. There is a lot of other devices. This was just the lines in kilometers. There is a lot of instruments. So what I'm trying to say that this is a big system. Previously, I claimed it was the biggest in the world, but Erik didn't agree because he claimed the internet. So, yeah, good luck internet. No power, no internet. But still, it might not be the biggest one in the world, but it's rather big, and it should always be remembered. I will come back to that later. It's a very important system. It's not just that we will lose internet for half an hour if the power systems go down. If we get a major breakdown in Sweden of the power, that is notable in the GDP of Sweden that year. It costs around 1%. Fortunately, we only have these major breakdowns once every 20 years. To some strange reason, the rules are that we're allowed to have one every 20 years. But in general, I will not go really into the detail why do we have them only every 20 years, because no one really knows, and it's another lecture. But in general, it's a critical system for the society, which means some parts has very high requirements when it comes to reliability of the communication system if they are depending on the communication system. Normally, in the power system, we consider communication system as something good that we can work with, but we have to survive without it because it's not good enough. But you should also remember that a lot has happened in the communication system the latest decades. We're talking about decades because we have a system that is built during many, many years. This is not something that you rebuild every 20 years. Economical lifetime of such a component is 40 years. Technical lifetime is 50 to 60 years. Some components survive up to 80 years. So an investment is quite long, which is another challenge. Because that means if we should introduce communication system, we have different generations of hardware, but we might also have different generations of communication systems. Because we can't, well, now we have a new version, let's replace it. Yeah, but it's a big thing to replace it. It's big and it's very, very expensive to do. What I also would like to say with this figure is actually that we have a very good system. In a good system, I mean that we normally don't have outages. We had 2 here in Gothenburg recently, which has been a little bit unclear why, but they are looking into it. What we actually see here is minutes of interruptions. On my language, this is called SIDI in general. So that is actually that you take the minutes of customer interruptions and divide them, the total number, divide them with the number of customers. And you see what we normally have. We have around 60 minutes, roughly, per year. In average, we are without electricity. This is, of course, not 60 minutes. I mean, it's not distributed evenly, because we know that sometimes things happen. We have already had some issues this year with Alfrida, the storm in the east of Sweden that will create some problems. And we also know what happens 2005 and 2007. We had big storms in the south of Sweden, and that, of course, has raised it. If we have big storms in the north, it doesn't impact that much because we have many fewer customers there. Because, as you might know, the majority of the Swedish people live in the south part of Sweden. So, therefore, a storm in the south part has much more impact here than the other one. They're, of course, trying to limit that, but it takes a while and it's a big thing to rebuild. I mean, they want to, this distribution, even though the majority is cables, they want to take a large part of it and making cable. But I mean, replacing 200,000 kilometers of cables, that's not really a small thing. Takes a lot of time and costs a lot of money. However, you're already paying for it because you might have seen that the cost for electricity has gone up. Not the energy, but this fixed cost that you pay every month has gone up if you pay that cost. I mean, I know it's sometimes included in the rent or you live at home, then you might not pay that bill. But if you have done that, you have seen that it has raised around 100% in the last decade. So a lot of things have happened because, and this has to do with the society expectations of it. So this was like a time step where we are today. So what is happening in the future? Because my idea here is to try to see where we're heading. Well, we have some paradigm shift in the society in general. And that has also come into the electric power system. First of all, we are going from central production and central things to a more distributed one. In power system, that means from large power producers like nuclear power, coal power, to more distributed one. Wind, solar, and those kind of things. I mean, in general, they're good, but we need to handle it. That also means that we go from controllable production, which in some way nuclear is, because we can turn it on and off. It's not very fast, but we can do it. We can do it fast also, but we're not allowed to do it in Sweden. But I mean, in general, we can control it. That will come, because then we need to cut that for wind power, for example. Of course, we can deregulate wind power. We can turn it off or reduce it. But the problem is we will not really save anything because there is no fuel to save. So we'll just waste it. But what happens on the other side is that we have more controllable loads. Now we're discussing need of communication, automation. Because nowadays we can actually try to use our loads to adapt to the available power. Because we need a balance, always a balance. So what we're looking for, instead of that one, we need to do this. Another thing that has happened that might help us, it's actually that the need for products are less. We want a service. Instead of having a heating system at home, you might want a comfortable temperature in your home. Okay, what is the difference of that? Yeah, since we're providing a service, we might be able to provide that service in different ways. We might be able to provide it in a way that is more adaptable, more controllable. So we can try to work. So therefore we see a thing that could help us. Then we have another straight thing. This really influences a lot of this on the build of power system, is that we don't have a power increase when it comes to people's electricity consumption. Previously, we always saw a gradual increase by approximately 2%. Which was quite easy, because if you calculate, if you have an increase of 2% for 40 years or 50 years, the lifetime of a line, and well, then you have the capacity up to, and then you increase 2% per year for 40 years, that means you will end up around a factor of 3. So previously, when we designed grid, we only said, what is the capacity now? Then you added a factor 3, and then you had a good system, easy to use. Because we know that the load increased gradually. But that is not really the case anymore, because today we are more step increases. 2 reasons. One is that we don't see a gradual because we are becoming more and more efficient. Yes, we get more devices, but they're also more energy efficient. So we need less electricity for them. We need less power because they are so good in general. But we also see that people, when we're building new houses, we don't open new areas. We try to squeeze them in. So when the load increase with a step because they add a new building or a new block where we don't have anything, except for that gradual low. I mean, then you can say, well, this is much easier because if that comes, we have to rebuild it. No, we can't rebuild it because it's so expensive. We have already invested this. We haven't really paid it off yet, and still we need to replace it. Sometimes we have to, but it makes it a little bit more complicated. But it also gives new opportunities, because if this comes, there might be ways for us to adapt that by controllable load, so we can live with this, because we don't know what is happening. If we just knew the size of the step and when they will come, that will not be a problem, but we don't know that. So if we try to squeeze it in a little bit more, so we end up in what we are just for the electric power engineering or the electric power systems. What are the main thing? Well, renewables I've talked before. They are coming both on the transmission level, which is main big things. We are talking large installation of wind power, 100 of megawatts, even gigawatts of installations, mainly in the north of Sweden. We see the same thing offshore. Maybe not in Sweden, but for example in the western part of Europe. But we also see a lot in the distribution grid, close to homes. And there we're talking mainly solar panels. So in general, how many think that solar panels are something good, that everyone should have at their home? We're like 5. Good. The problem with them is they create a lot of problem. Because today we have a system that is based, the distribution system is based on how we communicate or how we used to use electricity. And a big thing there is that we assume that not everyone is using power at the same time. Because if one is doing something, cooking at 1 hour, the next hour the neighbor is doing it. So they're not doing the same time. So we don't need capacity for everyone at the same time. So we kind of share the capacity. And that sounds good. However, solar doesn't really have the same. They have the same, but in a very different scale. So if you look on a distribution system inside a block, the problem is all solar panels in the same area, they are producing maximum at the same time. So you don't have this kind of factor that helps the two users. So in that way, we are losing a lot of the benefits, which means that when you're installing solar panels, you're also making it very hard for the distribution system. You might even break it. Yes, I have solar panels on my house. Just to say that. No, but I mean, of course, it's a good thing in general because we need more renewables. And it's also very good if we have it local. The power that is used either inside the house or to the neighbor, we don't have to transmit it long distances because it's there. So it's quite efficient in that way. So in general, it's good. But that's a big issue. Hasn't really reached Sweden yet, the problem, because there are still too few. And we have a system that is quite well sized due to our electric heating. But there is a big problem when it comes to the southern part of Europe. And how do we deal with this? Some kind of control is needed because replacing is extremely expensive. And if you should pay the updates of the distribution system when you install solar panel, well, you will kill any business for that in general. It's hard to make it happen anyway. And I have a payoff time of 15 years. And then I don't have to pay anything to the grid company. I just have to pay for the devices itself. I made the installation myself, so try to keep it down. Still took 15 years to pay it back, or will take 15 years. I'm not done there. And it's also a way for me to see what is actually happening. It was kind of a test on my own, so in that way. We also see a big drive for an increased energy efficiency in the whole chain to save costs, but also to save environment. That's in general good, but it also might need that we need to get more knowledge about what is actually happening. Are we doing the right thing? Are we doing the right thing at the right time? Which is another issue here. So we also have another thing, higher demand of electricity in emerging countries. I don't know if you've heard that they're saying that today we have 1 billion people in America, roughly 1 in Europe, 1 in Africa, and the rest then 4 in Asia. In 30 years, it will be 1 in North America, 1 in Europe, approximately, 4 in Africa, and 5 in Asia. So Asia will grow a little, but Africa will grow a lot. And they have practically no infrastructure when it comes to electricity. They have some, it's quite scattered, it's quite undeveloped. A lot of things is happening there. You could say, well, the problem with Africa is it's not a country, it's a continent. Lot of people we are talking about. So, lot of things is happening there, we need to do that. I've talked about the reliability and availability increased. We are expecting more and more of it. We also see more possibilities to interact with each other. We have the technical possibilities, but we don't. What we are looking for is, of course, this issue about politics in any way. Unstable regions, of course, we would like to interconnect with. An easy target is, of course, to use Sahara for solar panels. That would be very, very nice from many aspects. Well, the political situation in many of those countries are maybe not that stable that we would like to invest billions. I haven't really done the calculation, but I'm afraid it will be thousands of billions if we should have a huge impact on solar panels or solar power from Africa into Europe. But the resources there, we need more interconnections. But the problem is not the interconnection, the technology itself, it's actually the political issue. And we would find the money, that's not the problem. We also have more, and this is part of the solution, we also got more fast and reliable communication. And we can also use clouding computing. That means that we can use capacity, calculation capacity more or less everywhere due to this communication. We also got Internet of Things coming up, already there, depending on your definition. which also gives new opportunities because we can communicate with a lot of more things. More things could be part of it, could be more controllable, adaptable. But you'll also remember what are the consequences when we start doing things. It feels like, well, we just remove that because it's better for the system. Yeah, but what will be the consequences? Because what we're actually doing if we start altering in people's energy consumption is that we are impacting their life. Are they aware of that? That's a social question. That's an ethical question. Are we allowed to put requirements on electricity use on people? Do they really understand it? In general, I would say no, because we have a very low awareness of what we use electricity for and how much we use. How many of you know how much electricity you spend every year? Plus minus 10%. Of course, I know it. Part of my job.
I pay the bill, so
you pay the bill, so you look at it. I mean, I know there is a lot of people who pay the bill, but they don't really read it. Why? Because it's something that you have to pay anyway. It's a quite tricky thing to change, and it's a quite low. I mean low, you say, oh, well, it's hundreds of kronor. Yeah, but if you compare it to percentage of your income, maybe not as a student, but if you start working as an engineer, which is soon coming, then you will notice that the percentage is quite low, and you will also notice that if you start making things, you will not really get something back out of it. For example, I want to save, so I will not watch my TV show. I don't know if you watch TV, but take that as an example. So your favorite TV show, I will not watch that. So that is like 1 hour, 200 watts. We save that. That's 0.2 kilowatt hours. 1 kilowatt hour costs high numbers, 1 krona. So you're saving 20 öre for not watching your TV show. I mean, that's not much of a latte coffee. I mean, you can do a lot more for your economy by looking in for avocado sandwiches and coffee. So therefore, no one really cares because it's so cheap. And that's one of the issues here. So we have a system that we demand a lot, but we don't pay anything for it. That should be remembered. It's very hard to take any actions and make them affordable, at least for households. But we will have to try to do it because we might have to somehow. The problem is either we have to make it quite more expensive, taxes probably then, or we will have to make it mandatory in some way, which is another issue. So therefore there is a vision on how to do this and how to make it work, and that is try to interconnect the power system into a communication grid so that everything is also communicating. So we can try to always optimize our system. But again, big system, important for the society. We can't really afford things to go wrong. I mean, it's not the same consequence as an airplane, but still. It's not during major outages, not in Sweden, but in other countries, deaths are not uncommon, so to say. Because, well, you need it, especially for heating, or you're lacking something. You will waste a lot of money, refrigerator go down, freezers and those kind of things. But in general, the vision is to have a 100% renewable energy system with interconnections, advanced information and communication to optimize the system, to use it. And there we see money to spend, to save, but we also see environment. We have a big environmental driving force to do this. So it's not just something to save money. Be so frank, I don't see that we will actually save that much money. But we could decrease our footprint quite a lot. So, how will the future look like? Well, there is, of course, a lot of different ideas on how to realize this. How should we make it happen? I took this list from one of our professors, what he's looking into. There are so many of them, I can't really spend that much time on each, so I will select some of them to take them. But in general, controllable devices for power system to board, that is batteries, for example. Wide area monitoring, control, I will come back to this a little bit more, where we actually try to measure in the system in a very efficient way to actually reduce the number of protection systems or measurement systems. Try to do that. Condition monitoring and maintenance. It's another way, and that is actually to try to see what is happening to a certain device. Because as I said before, that we install them and they should be there for 50, 60, 80 years. And in the best case, we don't want to spend any time on looking up to them. So we would like to have some kind of conditioner-based maintenance. We also would like to know maybe some knowledge when it will break down, if it will break down. So we can have that ahead in some way. Here we see a big introduction of this digitalization or machine learning and those kind of new ideas here, because we need to know a lot here. The problem is that we don't really know the physical things happening inside the devices. So we might need help there from artificial intelligence. Dynamic rating I will come to. Microgrids, I don't know if you've heard about microgrids, but microgrids is a thing where you try to kind of make a small part of the system a little bit standing, not really alone, but it has some, let's say, less connection points to others. So you're kind of independent, or you can more rely on yourself and you can act together in a way. So you're kind of a bigger customer. He also used the word smart grids. I also know that you use the word here in the course, you talk about smart grids. I would say that is a little bit on the way out as a word, because it became very popular in 15 years ago, 20 years ago. The problem was no one really knew what it was. But it has gone in, I will come back to later, it's gone a lot about more communication, more efficient use. E-mobility, of course, electric cars, number one. But there is other things we're looking for. Trucks, boats, airplanes, a lot of things is happening there. Digital twin and digital substations, this is a way of how making what is today communication and protection system that are analog, that make them digital, instead to get more information out of them. We also have something called wireless communication. You have a lot of it in your everyday life, but in power system we don't have that. We don't dare, so to say, because reliability is too low. So there is a lot of fibers. I will come back to that later in that sense. But again, maybe in greenfield installations, or we try to work a lot on the two different levels. How to operate when we have communication and when we don't. And try to find situations to survive this low availability of wireless communication. And then we got something that is called virtual power plants. Have you heard of that? It's a little bit wrong name actually, because the idea was actually that if you are a small power producer, you have very hard to get into a market, you can't really do anything because you're always acting on your own. The idea is to have a virtual one where a lot of small ones goes together as one group and act as a big actor. Then this has evolved into loads. So there are like a lot of consumers that go together and act like one big one, and therefore could interact more, get better prices, be an ocean. Kundkraft. Have you heard of that? Yeah. They have some kind of advertisers on TV and stuff, so you might have seen them. And their idea is actually a lot of customers goes together and say, we want to buy power from or energy from someone, and then they negotiate for all the thousands of customers together, and therefore they will get a better price. So this is what they have. So virtual power plant is just small actors going together to try to be a big actor to act in the system. Otherwise it's a problem, of course. So this is happening in the system. I try to then put what is probably happening in the ICT. Where is the need and what do we have? Or what do we have and where do we see a need? I have made my own interpretation of these. I have divided system into transmission system, sub-transmission system, distribution system, and 400-volt system. That is local at home, what you have. From the last transformer, this concrete box that you normally see outside your window, to your house and including your house, should be remembered. Distribution system is that into the big substations, and then you have the transmission that is used to distribute it over the country. So this is increased in size. And then on this axis, this is a little bit tricky axis. because it's higher and lower depending on. The increased amount of data, I mean number of megabytes, will go up in this direction because we have so much more customers, more interconnections, more lines in this area. So there will much more data. However, the security demands will go down because what will happen here, we don't see a big security threat against a private household. We don't see any tourist focusing on one family building. That I will cut the power from that family. Because what will be the impact on the society? Quite small, I would say. Because that could happen anyway. Someone digs off a cable and then you're there. So it doesn't really matter. However, in the other end, it's a big issue. Because what will happen if we get a security breach in the transmission system? Yeah, we might lose power. Takes 1 day to restart. We will lose 1% of our GDP as long as they don't do anything else than just destroying our power system. You can also see risk of combinations here. I mean, what would happen if the thing happened at Drottninggatan in Stockholm? You might remember this terrorist attack. If they at the same time would do this in nighttime and they also cut the power in the whole country. Completely different scale. People would be much more scared and the impact would have been much bigger. Unfortunately, it's quite more tricky to do that than just driving a truck down this one. But the security is higher here. Demands on speed also go down because here we are using transmission for really things that are reliant in the transmission system to make it operatable without bringing down the system. When it comes down to here, we don't have the same requirement. We just need a lot of data, but it's not that important that it goes fast. It needs to come, but we can use internet, for example, which is quite slow compared to a lot of other things. However, you also see, so the demand of speed goes down, but the demand on integrity goes up. Because we have seen that if you measure the voltage or the current coming into a house, you can actually see what's happening inside the house in real time. I will take that as an example if there is time to do that. I spent a bit more time than expected. But what you actually see here is actually I've tried to put that transmission, what kind of communication is needed. Well, we have protection that needs communication. But now we are looking for protection to protect the system to not blow it up. And we know it's big investment, so we need a lot of protection. And they use designated fibers. They have fibers just for this purpose. Nothing else is allowed to use in this fiber because demand on speed is so high. It's also a security issue. But you solve both of them by having their own fibers because no one can really get into there. There is no physical connections to anyone else. Just between that connection point to the other one. Designated fibers.
Jimmy, can I ask you? So
yep.
With speed, you mean delay here, that you need low delays, not
yep.
high data rates? Correct?
No. I need to know if something is happening, it has happened also there. Okay, so and you need maybe you also need confirmation that it actually has happened. So it's not a lot of data. It's that we can't allow delays and we can't really afford mistakes either. And if someone else is there talking to it, there might be problems. So this is the problem. Then we have control and supervision. They have their own network, but then you might reuse parts of the system for different, control and supervision of other systems. But again, talking to a society critical system here. When we go down to the sub-transmission, we have the same issue about protection and super control, but here we have measurements also. It's of course part of this part. Where we have a lot more measurement here, and then they're using kind of shared networks. Many different solutions here. We are not down to internet, but still, you might share them with others. Not only within the system, but also with others. But still, it's not something public that everyone can use. So it's something. Distribution system, here you try to use shared separate network or kind of shared network for measurements. The measurements here are mainly for a little bit about billing purposes, because as well as you buy the electricity from your grid company, the distribution system buy the power from the sub-transmission system. So you have a stepwise. Right. So they need to do that. And there is no, you can buy that because it's not that, it needs to be accurate, but there is the value has to be accurate. But the speed is not that important because there is economical things that should happen afterwards. So it's not really in a hurry. So you have time to check and those kind of things. That is correct. And you can also look, is it, by having some kind of idea, is this a reasonable number? And we all know what is a reasonable number. But then we come down to this one, 400 volts. Here we have measurements, different kind of share networks, smart meters, but we also need a lot of communication with distribution company to customers, but also between customers, if we are talking about virtual power plants and microgrids. And we also see, or I see, that here will be the big increase in need, because this system is built. We don't need a lot more of those lines. Some lines, and there is a lot of arguments, hey, we need to build a new line to Skåne. Yeah, it's a minor thing actually. It's very expensive because the system is quite expensive. I mean, building a power line costs around 5 to 6 million per kilometer. So it's and you need maybe hundreds, 200 kilometers. So it's quite fast, goes quite expensive. So, but we see here is a lot of things that is growing, and I will try to look a little bit into these different levels. I first thought, what is old school? Old school, we have what we call a SCADA system. Signal condition and data acquisition. That is actually used in the transmission of subunit to just measure in the system and get it back. Do it for two reasons. Operational one, online, real time. Then we need some kind of operational data with a very low frequency. We don't need that information that often. What I mean we don't need it is because we can't handle it anyway, because that is someone sitting there. And for them it doesn't matter if they get an update every 10th millisecond or they get them every second, because in your head you can't process it anyway. So in some cases we even use 10-minute values. That's in general okay. I know 0.01 is a little bit higher than 10 minutes, but I don't want too many digits here. But you also use it for kind of alarms. And in general, yes, it's alarm, but they are not that fast. So it's a more reliable, we need to know what has happened, and there is not a lot of information here. So this is quite slow in general. It's not very accurate either, because we don't need that to know what is actually happening. We just need a big picture, so to say. Then we have the offline, and that's a completely different thing, because now we're offline, which means that whenever we get it, it doesn't report it, but it's a day to follow up. If something goes wrong, we need to study what has happened to avoid it happen again. Then we need kilohertz samples. And then we might need something for planning reasons, see what's happening. And then we're discussing up to seconds. Normally we don't talk about hertz, we talk samples 1 over hertz, so to say. The time between them. So normally 1 or 2 per second, or something. That is general enough. Sometimes if it's a big thing, we use hourly mean values. And then you can quite see that the communication there is not high requirement. So this is the old school. The problem is it's an expensive system because it requires a lot of measurement points. Because you need to measure everywhere. And if you want to know something, you need to install measurements, you need to install communication system to that point. Remember, the lines last 13 laps around the world. So it's a lot of lines. And you need to know that. So what is happening? When we are talking about transmission, sub-transmission, the big thing, now we are looking into what is called a phase measurement unit, or PMU. It's a quite simple thing in that sense. It measures voltage and currents. We have per channel, we have around 40 channels, 60 hertz. So you sample 60 times per second. And then you measure, as I said, maybe 24 or 36 channels at the same time. The problem with them, it's not really the issue of measuring, it's actually how do we know when it has been measured? Because these are used to see what is happening in the grid, and just looking in one point doesn't really say that much. You need to know what is happening between them. So what you actually need to know is what is happening in the south of Sweden at the same time what is happening in the north of Sweden. And the time difference is very, very short. And that is solved by using a GPS timestamp with a very high accuracy when it comes in time. So you know when it's happening. And then some do it what they call in real time. But I'm not really know about the definition of real time. I know it varies. You might have your own in this course. But of course it's not in real time, because since you need to read the measurements, it has happened anyway. But still, you can be quite close. But in general, these are mainly used for studies afterwards. See what has happened. How do we prevent this from happening? But it's a lot of data that comes. Then, so this is the device. It looks something like that. We got one in our lab. If you would like to see it, it's just a box. So nothing really to see, just a computer that measures. Then we use what is called a wide area measurement system. And this is actually to use this PMU in real time, that we try to collect data from many as possible and see what is happening. A lot of things could be done. Dynamic monitoring, see what's happening. Try to see disturbances when they're going on. What is happening? How are others reacting? Low frequency oscillations, or also frequencies below 50 hertz. We can see this kind of power oscillations going on in the system. Can we detect them and try to avoid them? Stability prediction, to see if something is happening in the system. Alarming, if something is going on. And this called state estimation, to see how can we actually see what's happening in point that we don't measure. That could be along lines. It could be things where we don't need to have a lot of different measurements. They're not that cheap. So it's a lot of things going on. And this is the idea of having measuring a few points and then calculate what is happening in between the points. And that's a big thing. And then you need a lot of data to have it. And of course you can always calculate. The problem is what is the accuracy of that, depending on what you're going to use it for. Distribution. Distribution is what we normally call smart grids. I will try to take some examples based on communication here. Some kind of introduction to it. I will assume that you will get the slides. I will send it to Erik when I'm done here. So you can read this. But you see, it's all about communication and how to make it work. And they are looking for both environmental issues but also for common, to make it cheaper, to make it more efficient in this way. But I think what it should be interpreted is actually increased efficiency of the infrastructure of electric power system. How do we use this installation? We know it's expensive, so how do we use it in the most efficient way? There are three main ways of doing that, according to me. Either we use new products, we use existing products for new use. For example, ICT is one. We have a lot of them, so why don't we use it in power system? It may not built for that. And then we have the hardest one, and that's new ways of thinking. If we do things in a new way, it has very little to do with communication, but it might require communications to take new decisions. This is generally the hardest part, because thinking in new ways is way much harder than just introducing a new device. Everyone likes new devices, but no one likes to think in a different way. So then we have the smart meter, and this is the distribution system PMU, so to say. Every one of you has one. You don't own it, but every meters in Sweden nowadays are smart meters. And the idea is actually that they measure every hour and send information. I say every hour. And they send information to distribute. Now they're looking for requirements to put it into every 15 minutes of consumption data to our customers. Used mainly for billing purposes. And it's a law in Sweden since a few years ago. So the idea why we have it is to understand the consumption, but we also can use it to understand the behavior in the distribution system. But that will require data and analysis, quite a lot of it. I have to skip that one. Dynamic rating is also a quite nice thing to look into and give opportunity for, and that is actually the opportunity to use the maximum of the system. Because today, since we have systems that always have to work, I mean, it costs if it goes down. The idea is actually that that then we size it so it can have the maximum load during the worst conditions. Maximum load in Sweden we got during winter nights, because then everyone is used electric heating. Good. So we need to, that is the maximum current. And then say, when is the maximum temperature? Well, maximum temperature is during summer, because we have to find the worst case. But the problem is they never happen at the same time, or almost never happen. So the idea is to do some measurements. Here are some data about it. I've lost time here. Which means that there is need for more communication, more measurements to see what's happening, and based on this, try to use the infrastructure as much as possible. It could also mean that if you know you end up in a limitation here, you might have to reroute the power somehow to use the system more efficient and still supply the load. I have to look there. And then we have the local one. About how do we act in the local system. Now I'm talking close to you, in your home. What can you do? And what is the requirement of speed? That is actually up to you. There are systems for monitoring. This is Lect, for example, who has this kind of system where you can install it. I have one at home. There are also different types of home automation systems. A lot of them. You can buy them at Clas Ohlson, Jula. Loads of them. And a lot of other places. You can buy them to be able to monitoring and control your own consumption. But still, it's one device per thing. So you don't really use any artificial intelligence to understand what is happening in the system, even though we might be able to do that. And this was actually, I did a thesis work on this, where you actually took pattern recognitions of the power and the current to see what's happening inside in the house. That could be very good, because you can see what's happening if something goes wrong in our home. But it can also be used for supervision. Integrity. Is this a problem? Yeah, of course, because then can see people what you're doing. But it also gives me, as a house owner, a control of what's happening in my house. I got kids. So now they're a little bit small, but when they're old enough to come home by themselves, it could be very good for me to know, because the system would notice when they get home, because things is happening. Today I got an alarm that could maybe solve the same thing. But still, this is one way, and I don't have to have any other devices doing it, because it's just measuring here that we are someone doing again. But we can also have other ideas, for example, helping elderly people. Because we know that people are they are creatures of habits, which means that if they're not doing what they're supposed to do, something is wrong. And we can go there and help them. Instead of having cameras, taking pictures of them all the time, which is very, very close to see what's happening. Then you might know, I mean, if Agda hasn't put on her coffee 8 in the morning, as she has done the last 50, 60 years, something is wrong. Someone need to go there. Instead of having a picture, see her laying in the bed. You can notice that in a more discreet way. So there is a lot of things that can be done by looking into this. And then we have this power plant, and here we come back to what I mean, as fast as you want. Because as a single actor, you have very hard to interact with others, because you have very little to offer in this case. But if you are, the more you are, the stronger you are, because the bigger actor you are. And you can look for you and your neighbors, you and the block, and the whole city. And the faster you react, the higher is the value of your service. Because you can do fast changes to solve problems that occur rapidly, so to say. So therefore, the value of your service will go up the faster you react. And that will, of course, put higher requirements on the need of communication. But the problem is, how should it work? What kind of information needs to be shared? What do people want to share? Who should operate and handle the data? Big issues, of course, because now we're talking close to you in that sense. I know I'm late. I just want to bring into threats. I have very little on that. But we see a lot of things coming up now. I took the example earlier. What happens if it goes wrong? There is, of course, the problem that we don't get any data. That is a case that we are quite well prepared for, because we know that sometimes communication doesn't work. A worst case is the other one. If someone is feeding the operational system with false data. So they're actually intervening in the system and making us do things that will destroy the system. Eavesdropping is, of course, another issue, what is actually happening in the system. And then it could actually go into control by others to prevent things from happening, and thereby creating chaos in other parts of the society. So what is the level of the security? She had to resign yesterday due to this. Typical scandal in general. They had some problems with their IT system or automation system, so they hired someone to do it. So, and it became a US company, and they forgot the security requirements. So for 1 year, they run the system without any security clearance of the technicians handling the system. So now SAPO, Security Police of Sweden, will try to look into that, and she has resigned. She had to do it because it was not, let's say, not a good way. So I would say we're not really prepared there. We don't know what is happening. So far, nothing has really happened either. I mean, even though we have had unlicensed people looking into our power system by having it controlled, nothing big has happened as what we are aware of. We can't really trace any big accidents to someone coming in and destroying things.
But it could happen, right?
It could happen.
Somebody could collect data for the right
Yeah.
to destroy the system.
So they could have already stopped on the thing that is happening. I mean, they have a lot of requirements to get the hardware data. I mean, I don't have a clearance from SVK because they haven't considered me needed to do that. So I have only foreseen different kinds of maps. I'm not allowed to bring them at home or with me, but I can see them during meetings with SVK. So the hardware, I mean, data, where the line goes, how big they are quite well protected, but on the communication side, they seems like beginners. Sorry for that. It was 5 minutes too much, and I have missed some parts of it. Of course, I will send you the slides to Erik, and he will distribute them. And if you have questions, you're always welcome. Come back to me. I'm not an expert in all these areas. Some parts is better than others. I try to give the overview, and I hope you have got some kind of insight what is happening. A lot of things is going on in the grid, so we need something new, and then we will use communication to make it more efficient, because we can't really afford to do anything else. New opportunities will arise, but there will be very different requirements on the communication system. Some needs to be fast. Some require high security. By fast, I mean mainly no delays, not a lot of data at the same time. Some of the communication needs to be understandable by all. And here I mean by all. Not, oh, they have just a 2-year engineering degree. I mean all. People that don't care at all, they need to understand what is happening. Because we need to get everyone aboard if we're going to solve this greenhouse problem. Or at least do the power system share of it. This has to be reliable and cheap, and secure, of course. Yeah? I've been talking for 50 minutes now, but do you have any questions? I guess you have a lecture at 11. So,
no, we'll take 15 minutes.
Yeah, we will take 15 minutes. I will be here if you have any questions. And otherwise, thank you.
Thanks, Jimmy. This was interesting.